Today we'll be doing the integral from 0 to infinity of the natural log of x cubed plus 1 divided by x cubed dx. And to start off, we could parameterize this integral. So we could rewrite this as the integral from 0 to infinity of the natural log of yx cubed plus 1 divided by x cubed from y equals 0 to y equals 1. So we could rewrite this as the integral from 0 to infinity and the integral from 0 to 1 of 1 over x cubed times the partial derivative with respect to y of natural log of yx cubed plus 1 dy dx. The integral from 0 to infinity and then the integral from 0 to 1 of 1 over x cubed times 1 over yx cubed plus 1 times the partial derivative with respect to y of yx cubed plus 1 dy dx. So we have the integral from 0 to infinity, and then the integral from 0 to 1 of 1 over x cubed times yx cubed plus 1 times this partial derivative related to x cubed times dy dx. And as you can notice, the x cubes cancel, and we're left with the integral from 0 to infinity, the integral from 0 to 1 over yx cubed plus 1 dy dx. So we now have that our integral is the integral from 0 to infinity, and then the integral from 0 to 1 of 1 over yx cubed plus 1 dy dx. And from here we could exchange the order of integration. So is equal to the integral from 0 to 1, and then the integral from 0 to infinity of 1 over yx cubed plus 1, and it's going to be dx dy. And from here we can make a substitution. We'll let u equal yx cubed, and we'll solve for x. So x cubed equals u over y, which means that x equals u to the 1/3 divided by y to the 1/3, which means that dx equals 1 over y to the 1/3 times the derivative of u to the 1/3. So we have a 1/3 u to the 1/3 minus 1, which is 1 over y to the 1/3 times 1/3 u to the negative 2/3 du. So that's our dx. And the bounds of integration, u sub 1, when x is 0, u1 is 0, and u sub 2 will tend towards infinity, so the bounds do not change. And we're left with the integral from 0 to 1 and integral from 0 to infinity. 1 over yx cubed is u plus 1, and dx is 1 over 3 times y to the 1/3, and then a u to the minus 2/3 du, and then don't forget the dy. So this is equal to 1 over 3 times y to the 1/3, the integral from 0 to 1, and then the integral from 0 to infinity of u to the minus 2/3 divided by 1 plus u du dy. And from here we can make use of the beta function, and we'll let m minus 1 equal negative 2/3, and m plus n, well, that's just going to be 1. So we have that m is negative 2/3 plus 1, which is equal to 1/3. We have n equals 1 minus 1/3. So we just now have that we have 1 over 3 times y to the 1/3, the integral from 0 to 1 of the beta function of m comma n, which is 1/3 comma 1 minus 1/3 du, and that would be just dy. And this is a special case of Euler's reflection formula. So we have 1 over 3 times y to the 1/3, the integral from 0 to 1 of pi cosecant of pi over 3 dy. And if we recall that the sine of pi over 3 is the square root of 3 over 2, which means that the cosecant of pi over 3 is 2 over the square root of 3. So this is 1 over 3 times y to the 1/3. The integral from 0 to 1 of pi times 2 over the square root of 3 dy. Could we write this as 2 pi over 3 times the square root of 3, the integral from 0 to 1 of 1 over y to the 1/3 dy, which is equal to 2 pi over the 3 times the square root of 3, the integral from 0 to 1, y to the minus a third dy, and that's a standard integral. We'll use the power rule. We have 2 pi over 3 times the square root of 3, y to the minus a third plus 1 over negative a third plus 1 from 0 to 1. So I have 2 pi over 3 times square root of 3, y to the 2/3 over 2/3, but that would be 3/2 from 0 to 1. And we see some nice cancellation. The 2's divide to 1, the 3's divide to 1. And we're left with pi over the square root of 3, y to the 2/3 from 0 to 1, which is equal to pi over the square root of 3, 1 to the 2/3 minus 0 to the 2/3. So this is clearly 0 and this is 1. So we're left with pi over the square root of 3. So in the end, we have that our integral from 0 to infinity of the natural log of x cubed plus 1 divided by x cubed dx equates to pi over the square root of 3. And that is the final result. Thank you very much for watching.